Our second application of work problems are lifting problems. If work is force times distance, then one of the most common forces we have to contend with is gravity. So therefore, lifting an object has a lot of work involved, right? Because work is generally force times distance, and force is gravity. Now, you might have learned somewhere along the line in science that if you take an object like a rock up to the moon, it has the same mass, but it doesn't have the same weight. Weight is the force due to gravity on an object. So it's the mass times the gravitational constant. So you take your mass, like say in grams, and you multiply it by g, which is the gravitational constant of 9.8 meters per second squared. All right, so then that means that we can compute the amount of work required to lift an object vertically against the gravitational force, because work would be force times distance. Force would be our weight. So when you have weight, like pounds, you actually have a force right there. And then you multiply it by y, because your distance will be in y because you're lifting vertically upward. So therefore that distance would be y. All right, so let's talk about lifting a chain. The total work to lift a chain that stretches from the height of L, right up here at the top, all the way to the ground. Now we're going to assume that it has a constant density. That's actually a pretty safe assumption. I mean, it's a chain. We're not assuming that, this part is more dense than this part for any reason. So it has a constant density. And then what we'll do is we'll take little sections. So you'll have L minus Y, let's say right here, L minus Y. And then you're taking like little sections dy, which is right here. And of course, well, I went a little smaller than they did, actually. I'm going to go that small. All right. So I have my delta y, and I have rho, which is my density, times gravity, which is g. And I'm lifting this section of the chain, L minus y, because this is y right here. Right here. Right, there's y. And then you're lifting it L minus y. That's how much you have left over to lift. Right, so if you're talking about this section of the chain, you have L minus y to lift it, and that's true for each of the sections. And of course, we're going to take the limit as n goes to infinity. We're going to let the number of sections in this chain be infinite. And if that happens, well, what you think is going to happen happens. So you'll be taking the integral, because all of this turns into an integral. Because instead of doing a discrete section by section adding, you're going to do an infinitesimal section by section adding. So you're going to start at A down here at the bottom. Or, well, I shouldn't say that. It could be from anything to anything. So if they don't say you're going to lift the whole chain, if they say it's the whole chain, you'll go 0 to L, right? But if they don't say the whole chain, then it could be just, hey, I want to go from this point to this point, from the second floor to the third floor, or something like that. Well, then you'd use A and B. Of course, it'll be rho, because rho is constant. It'll be gravity, because gravity is constant. And then you'll multiply it by L minus y, because that's how far you have to lift any particular section. And then your delta y will turn into dy. Now, note, and let's just make a little note here. If you're lifting the entire chain, from the ground to the height L, from ground level to height L, A would be 0 and B would be L for this integral. And that integral is also written down here as the definition of work done by a lifting force. Now we can use these for ropes, for cables, for chains, all of those kinds of things. So you imagine it hanging off the side of a cliff or a building or a ship, and this is how much work is done to lift that cable or chain. By the way, notice it's also assuming that it's hanging freely. for its entire length. We're not assuming that it's laying against, I don't know, a scaffolding or something for part of it, because that scaffolding would take part of the force and part of the weight. So we're just assuming it's hanging free. So now let's apply this to a couple examples. We have a 60-meter long, 9.4 millimeter diameter rope hangs free from a ledge. The density of the rope is 55 grams per meter. How much work is needed to pull the rope to the ledge? All right, so I vote we make a drawing. I've been longing to draw a stick figure. All right, so we have this ledge. We have a person up here, stick figure person. And then they have a rope that is hanging off the edge. Rope. Okay. Now they tell us that it's 60 meters long, right? So they tell us that, well, let's see, it was needed to pull the rope to the ledge. So it's saying it's hanging free from that ledge. So then we're going to assume that this is 60 meters. It's a little weird, but it's kind of written that way. Right? All right, so then the density of the rope is 55 grams per meter. Wonderful. All right, so let me write this out. So work is equal to the integral from A to B, rho G L minus Y dy. Okay, no problem. So let's see here. We want to lift the entire rope. So since we want to lift the whole rope up, let's see right here, pull the rope up. So since we're going to pull the whole rope up, that means that we're going to go 0 to 60 right there. Now, rho is our density, and that density is right here. It's 55 grams per meter. I guess we can make a little note. It's grams per meter, right? If you want to check your units, that's one thing you want to be careful of, because sometimes they'll be sneaky and give them to you in units that don't quite match, and you have to convert them so that they do match. But this is grams per meter, so that's wonderful. Gravity is gravity. So gravity is 9.8 meters per second squared. So 9.8, and you can make a little note. That's meters per second squared. So the meters there would cancel, which is good. And then we have L minus Y, right? So L minus Y is right here. Sorry, I'm just choosing my color here. All right, so L minus Y, that's the distance from wherever a particular section is. So if I say, this is Y, this is L minus Y, and that's Y, right? That's just the nature of the beast, right? And that's Y. And then this is dy, delta Y, which turns into dy, right? If it's infinitesimally thin. In fact, I'll just say dy. There you go. Okay, so then L minus Y is a distance. So that's measured in meters. And that would be 60, take away Y, right? Because our L was 60. And then dy is delta Y, dy, and that's a change in vertical distance, which is also in meters. So even though these two meters cancel, we'll be left with grams times meters divided by seconds squared. So grams meters squared over seconds squared. We'll get there. All right, so now let's find this integral. So 55 times 9.8 is 539. I'm capable of going to Desmos and finding things like this out. So that's 539, those two right there. Here, I'll just put a little underline so you can know where that number came from. And then I'm going to integrate 60 minus y, because that's a constant, but it's inside of a term or a binomial here, so I can't break it out like I could the 55 and the 9.8. So the integral of 60 is 60y minus 1/2 y squared. And then I'm going to take that integral from 0 to 60. All right, well, 0 won't be relevant because here, I'm going to do this over here. 539 times, and then it's 60 times 60 minus 1/2 times 60 squared. Well, that's 60 squared minus 1/2 times 60 squared, so the whole thing is 1/2 times 60 squared. I mean, you can just grab Desmos and find it. It's 539 times 1800. 60 squared is 3600. So 3600 take away 1800, which is 1800. And again, I use Desmos, and it's 970,200. Now the units would be grams times meters squared over second squared. Right? Actually, let me just say it's grams times meters times meters. Let me write it that way. I'm going somewhere with this. Right? There, I just changed it to match the colors above so you could see. All right, so these meters in here canceled. So, but it's grams in orange times meters in purple divided by second squared because there's a division there, and then another meters. Now, where am I going with that? What's my point? But this right here is the unit for newtons. So what we have is 970,000 Newton meters, aka joules. Right? So it works out. So this is 970,200 Newton meters, or if you like, 970,200 joules. All right, let's do another one. So we have a ship's anchor weighing 800 pounds. It's attached to a chain that weighs 10 pounds per running foot. Find the work done by the winch. Oh, this is going to be terrible. Because it's in pounds. Never as good. You can always tell. Physicists always use real metric, but you know, sometimes the math books use English system still. All right, so well, now it's the American system. The English gave it up. All right, so the work total, let's think about this, would be the work done for the chain plus the work done for the anchor, right? So you're lifting this chain and it has an anchor attached to it. But the anchor doesn't vary. The anchor is constant. It's not changing. The chain changes because as you lift, more and more of it's piled up behind you and you have less and less and less to lift. So the work that you're doing starts off really large and gets less and less as there's less chain dangling, right? But the anchor is constant. It does not vary. Constant work. Does not vary. No matter what, you're lifting 800 pounds up 20 feet to a height of 20 feet. Interesting. Now this one does vary, right? Okay, so then that means that the chain is going to need the integral. So we're going to have to do an integral for the chain. So there'll be something in there and then dy. So we'll be back for that. So that's the hard part. The anchor, however, is actually quite easy. Work is force times distance. The force is 800 pounds and the distance is 20 feet. Done, right? So this is force, this is distance. That's it. I mean, if you go back and look, weight is a force, right? Mass times gravity, but when you have pounds, you already have mass times gravity. Pounds are mass times gravity. Right, because they're a weight. All right, so then the chain. The chain will be, let's think here. We need the integral of force times distance, right? So we need density times gravity times the lifting point. But density times gravity will get us weight, which we already have. So this piece, the rho g part, we're going to get from the 10. So they told us that it was 10, and let me just put in the units here so we can see it. It's pounds per foot. And then we're going to lift it 20 feet. So it's 20 minus y, which is in feet. So those feet will cancel. And then times dy, which is also in feet. So we have our weight per foot, which is basically getting us our force, right? Or if you like, our density times gravity, right? It's already right there. Pounds is easier to work with in that way. We have less to do because the g doesn't enter into it. G is already part of that 10. And then we're lifting it 20 minus y. And then, of course, we're lifting the whole thing. So we're going to go from 0 to 20 here. All right. So that would be the integral of, well, I can just pull the 10 out. And the integral of 20 is 20y minus 1/2 y squared, or if you like the antiderivative. And then I'm taking it from 0 to 20. plus, and this is just going to be 16,000 done. And if you want us to know the unit here, I guess I should have put here. I should have done it this way. I'm sorry. I can just go pounds times feet. And you can see it's going to be foot-pounds. If you've ever heard of foot-pounds as a unit, that's what it's going to be. Foot-pounds are a unit of work for the English system. It's also in your backup sheet for definitions. Just real quick. Measurement of work, foot-pounds. So there you go. All right, so then let's integrate this. We already did, so let's put 20 in. So 0 doesn't do anything, so we only care about the 20. So it's 10 times 20 times 20 minus 1/2 times, oh, there it is again. Same number, minus 1/2 times 20 squared. And then if you like, it's minus a 0, but we don't really care about that. And then plus 16,000. This is 4,000, or excuse me, 400 minus 200, so that's 200. So 10 times 200 is 2,000. Again, you're welcome to double check me on Desmos if you so desire, but I'm right. And that gives me 18,000 foot-pounds. Because both of these ended up being in foot-pounds. If you look up here, the feet there cancel, and you're left with foot-pounds, foot-pounds. And so you're able to multiply them, and that's your unit of work. Now, if you were given the problem in kilograms and meters, how would the calculation change? Well, kilograms is mass, and meters obviously is length. So you'd have to use gravity. We'd have to put in the gravitational constant ourselves. It's 9.8 meters per second. Meters per second squared, sorry. It's a accelerational force, right? Okay, so if you're given the problem in kilograms and meters, you're going to have to use 9.8. When you're given feet and pounds, you didn't, because gravity is already part of this problem right here. It's already figured into the fact that it weighs 10 pounds. So gravity is already taken into account. Oh, let me just say, with pounds, gravity is already taken into account. Oop, if I could spell the word account. Oop. I'm running, it's just because I'm at the end of my page right there. There we go.